Welcome back, those of you online, and now Stephen is going to continue. Thank you very much, Stephen.
Okay. So yeah, thanks again for being here. I know you didn't sign up for this. You signed up for braids and configuration spaces, and the schedule on the website said this would also be like a 2-hour thing, just like the grad school. I will definitely not do that. So let me just finish, I don't know, maybe another 10 or 15 minutes or something by finally stating a theorem of Ben and myself. So this is what I just told you. People have been identifying bigger and bigger classes of simplicial complexes for which the moment angle complex can be identified as a wedge of spheres. So in particular, these all imply that the corresponding Stanley-Reisner rings are Golod. And I haven't given you definitions of all of these like combinatorial classes of simplicial complexes. And instead of doing that, I'm going to think of all of them in a very different way. So none of these results use a certain classical result in commutative algebra that says that simplicial complex is Cohen-Macaulay if and only if its dual has a linear resolution. So here I'm saying the dual is Cohen-Macaulay if and only if the Stanley-Reisner ring of the original thing has a linear resolution. And to have a linear resolution, there are lots of ways of saying it, but it just means it's the minimal free resolution as an S module. S, where S, remember, is our polynomial ring. So I'm always thinking of this as an S module. One way of saying it is its Betty table is concentrated on a single strand called the linear strand. You'll sort of see what I mean even if I don't give a definition, but this means something like there exists a number D such that all the, okay, forget that. Definition, quick definition of a linear resolution. So beta ij of the Stanley-Reisner ring just means the ijth bigraded component of Tor, the Tor algebra of the Stanley-Reisner ring. The dimension as a vector space of the homological degree I part of this thing. We look at the minimal free resolution of an S module, thought of as a graded S module, right? S is some graded ring. So it's a resolution in the usual sense, so it has a homological degree, but each object in the resolution is a graded S module, a free graded S module. So the internal degree is the second bigrading here. So people study the Betty numbers of rings by writing out these Betty tables. And if your ideal is generated in like degree D or D plus 1, then these are all 0 for J less than I plus D. The first place you can have anything is there. And we say you have a linear resolution if that's all you have. So like sort of saying it's as simple as it possibly could be. Everything is concentrated along one strand or one row in the Betty table. Another way of saying it is if you write out the minimal free resolution of the S module, then, okay, that's just a sequence, exact sequence of free S modules. Their ranks are exactly these things, the dimension, this Tor, and the maps between them can be thought of as matrices, right? And if all the entries, all the non-zero entries of your matrices are just linear terms, just monomials of degree 1, then you say that's a linear resolution. So the simplest thing that could happen.
So you mean that the generators of the phase ring are in degree 1, yes?
Generators of the face ring. Well, there's only one generator here, that 1 in degree 0.
Oh, sorry,
So the generator of the polynomial ring, those VI's are in degree 1, right?
I said 2 earlier. Let's maybe
Yeah,
stick with,
but then
or 1 is fine.
but then that shift wouldn't work as it's written if it's degree 2, right? That's why I'm asking you. So that J doesn't equal to I plus D, that would correspond to taking.
Yeah, you might put a 2J.
Yeah. That otherwise you'll have to put 2 J's if they're in degree 2, yeah.
With the standard grading here, where all these have degree 1.
Oh yeah,
put
okay.
all that. Yeah, you can think of like putting a different than standard grading here, or you can think of the isomorphism between the cohomology of ZK and this thing as the isomorphism is changing this grading around. So yeah, either way. Okay, thank you. So what's the point? So here is our sort of different approach to this. First of all, we have this torus action. I said we understand cohomology of ZK. And because it's just given by this Tor algebra, that's like saying to know the cohomology of ZK is just like knowing the modules in a minimal free resolution of your Stanley-Reisner ring. So all the rest of the data, we want to hope to read off the homotopy type of ZK, the combinatorics of K, or from the homological algebra of the Stanley-Reisner ring. We just need to understand the maps between these things, right? Just the cohomology groups of the Betty numbers alone do not determine a ring, and they will not determine the homotopy type of ZK. So let's bring in this group action that came with it. So this makes cohomology, or let me switch to homology now, because I want to talk about the Hurevich map. This becomes a module of an exterior algebra. So let me write lambda on little lambda 1 through m as the homology of our M torus. So these lambda i's, degree 1. And notice when I dualize from cohomology to homology, this instead of Tor, I should maybe write X over our polynomial ring. And notice an exterior algebra, Kazul dual, or it's like X of just the ground field. So this exterior algebra action on here, which is coming from something topological, the torus action, can be shown to be exactly the sort of standard algebraic action of this thing on this thing, the Oneida product. And then this can also be understood in terms of the Hochster formula. So under this Hochster interpretation of the cohomology or homology of ZK, so this would now look like a big sum over all subsets of our vertex set. We reduce homology of full subcomplexes. This action can be understood very concretely in these terms as well. So under this isomorphism, acting by like lambda I, right? Just shift homology up. Give some map like that, whatever this exterior algebra action is. This turns out to correspond up to sign anyway. To just some maps you get that are induced by inclusions. So you could take any full subcomplex I and you could just look at its inclusion into a bigger full subcomplex, namely the one on the vertex set I union little I. And that's going to induce a map like this. So since it's just induced by an inclusion of simplicial complex, that's like a degree 0 map, but there's some shifting going on in this isomorphism. So that ends up giving you a map of degree 1 here. So that's exactly what this action looks like combinatorially. Okay, so this action gives us a module structure. And now consider the Hurevich map. Homology of ZK with any coefficients. And we always have the Hurevich theorem that says like the lowest topological degree here is always in the image of the Hurevich map, the first non-zero homology group. But the homology of these spaces are identified with this X thing, which has a bigrading. And it turns out the lowest like homological degree in terms of X is also easy to see in the Hurevich map. So about the only thing that's obviously in the image of the Hurevich map is the following. So for each minimal non-face, I is not a face of K. A minimal non-face just means every proper subset of I is in K. So it's like a missing edge or a missing triangle or an empty simplex of some dimension. For each such thing, you could look at the full subcomplex on that vertex. Because it's a minimal non-face, it's just going to look like the boundary of a simplex. So this is looking like the boundary of like a I-1 dimensional simplex sitting inside K somewhere. And you could just consider the inclusion of that small induced subcomplex into the whole thing. And that's going to induce a map of moment angle complexes. And we already decided as our first example that the moment angle complex associated to the boundary of a simplex is a sphere. So each such thing induces a map I'm going to call omega I, and that'll go from Z K sub I, which will be, so it became like a 2n plus 1 sphere. So twice this thing plus 1 is going to be whatever 2i minus 1 sphere. So there's one sort of obvious way of constructing a map from a sphere into your moment angle complex. And it turns out it's not hard to see that there are Hurevich images. H maps give a basis for X1. Right, so that's sitting inside of the homology of ZK. Yeah, so the homological degree 1 part of X does not have to be at like the very bottom ZK, right? You could have a missing edge somewhere in K that's giving you a degree 3, topological degree 3 causing here. Missing triangle will be a higher dimensional thing. So these classes can be sort of spread out topologically in this space. So those are all spherical. That's about all that's obvious. So define now using the module structure above. A quasi-linear strand. Stanley-Reisner ring, which could be denoted like this, Reisner ring shriek, to be just the lambda module, exterior algebra submodule of X, or of the homology of our space. Generated by these classes, by X1. So this notation is supposed to suggest Cazul duality. If you know about classical Joule duality for quadratic algebras, A is any quadratic algebra. Cazul dual ends up being a sub algebra of its Oneida ring. So X A is like a graded algebra over the field K. called the Cazul dual of an algebra, and then your algebra A is called Cazul if this thing just exhausts this whole Ionide algebra. So there's a whole analogous theory of Cazul modules. So our algebras, like if you thought of a Stanley-Reisner ring as an algebra, it's usually not a quadratic algebra, but it is a module over a polynomial ring. It is a module over some quadratic algebra. There's a notion of a Cazul dual. That's roughly what this is. So we would say this thing is a Cazul mod. The Stanley-Reisner ring is a Cazul module as a module over S. If this submodule generated by the lambda algebra is just all of this, or all of the homology of ZK. So topologically, this is like taking these classes we just defined, which are in some sense sitting in the bottom of this space, just acting by the torus action and seeing how high they go. Turns out that they often just exhaust the entire space. Okay, so briefly, show is that for just any k, Hurevich image should just mean the image of the Hurevich map, some coefficients. Always contains the quasi-linear strand. I warned you I'd be overusing this word quasi. And just very brief idea of that proof. Maybe before that, I should have said something. I won't write this down, but in case your Stanley-Reisner ideal, Stanley-Reisner ring is generated in a single degree, so meaning all your missing faces are of the same size, then this just agrees with the linear strand, what's usually called the linear strand. And so that corresponds, this thing exhausting, the linear strand exhausting all of this is exactly what it means to have a linear resolution. This is just something slightly more general. Your Stanley-Reisner ideal does not have to be equigenerated if one can speak of a quasi-linear strand. Okay, so the idea I think is simple. I'm not going to write much here, but uses just a little bit of structure. We have this lambda module structure, first of all, on homology. And we have Whitehead products in homotopy. So this gives homotopy of any space the structure of a sort of graded Lie algebra. So we just look at this fibration at the beginning. Prove something more general than the statement of this theorem, was just that if you take any map, any element in the homotopy type, in the homotopy of ZK, and then you think of this space, remember this Davis-Januszkiewicz space just sits between the m-fold wedge of CP infinities and the m-fold product of CP infinities. So it's got m bottom classes in degree 2. We can include S2 in there, m many different ways, just the bottoms of CP infinity, m times. Or they're just the bottom cells here that lift to here. And what we show is that, okay, F is just in homotopy of ZK. So the Hurevich image of F, that's in Hn of K, right, degree n homology class. And then if I act by one of these generators like lambda I, that gives me some element in Hn plus 1 ZK. So we identify that with the Hurevich image of something in Hn plus 1. look at this picture, there's sort of only one obvious thing to do. So I can call this map omega. I could compose F with omega. Now I have two maps from the sphere to the Davis-Januszkiewicz space. I could take their bracket there, their Whitehead bracket. So here's mu I, same I as this lambda I. And the composition F omega. So that gives me a homotopy class in here. And notice that the base of this fibration is an Eilenberg-MacLane space. So anything is going to map trivially down here in homotopy. This is like a k pi 2 classifying spaces of tori. So this thing is going to lift through here, and it lifts uniquely. This fibration like splits. I keep going this way. So there's a unique lift, or sometimes called a relative Whitehead product, right? If you have a map into the total space and a map into a fiber, this is a standard way of getting a new map to here, some sort of Lie algebra structure. So the point of this little equation here is just that the Hurevich image is closed under this lambda action, right? If I take any spherical homology class, like H of something, and I act by lambda, I get H of something else. So Hurevich image closed under the lambda action. Okay, let me not write any more, but the idea, if you look at this definition, quasi-linear strand just generated by the lambda action by these X1 things. We said X1 is about the only thing that's obviously in the image of the Hurevich map. So the entire linear strand must also be. So this automatically implies that if you have a linear resolution, then the Hurevich map is surjective in all degrees for that space. Okay, so maybe I should just write one or two more things. This recovers the most general result over there of Irie Kishimoto. Let me say sequentially Cohen-Macaulay, whatever that means. So just use the theorem above together with Egan and Reiner. Is that still over here? Yes. And Reiner says the dual is Cohen-Macaulay if and only if you have a linear resolution. And Irie and Kishimoto give a slight generalization, but this classical results in commutative algebra has many, many variants. People have stretched this and generalized it in all kinds of different directions. And one direction covers this sequential Cohen-Macaulay class. So use either Reiner or respectively a result of Herzog, Hibby, proved in the 90s. Saying this is Cohen-Macaulay, respectively sequentially Cohen-Macaulay, if and only if standardized ring of K has a component-wise linear resolution. So this is just a generalization of the notion of a linear resolution where you don't have to have all your generators in one degree, the generators of your Stanley-Reisner ideal. But the exact same way, if you have a component-wise linear resolution, then the quasi-linear strand exhausts the whole thing. Okay, and this recovers a few other results. Notice I'm not saying that the quasi-linear strand is everything if and only if your component-wise linear. It turns out quasi-linear strand equaling this is a bit more general, so you generalize the results a little bit beyond this class. but it recovers another result that was out there in the literature. At least I've seen it in a paper of Beeben and Gerbich. They talk about homology missing face classes, HMF simplicial complexes, and they showed moment angle complexes wedge of spheres, but they did not sort of situate it in this context. But it follows from this that their class HMF, whatever that means, is slightly bigger than this class. So it sits at the end here, and this also covers that. Okay, so I'm really done, but part of the idea was of this was not just to recover these results, but to prove, a general theorem that just holds for any k that might be useful beyond this case of trying to understand when you have a wedge of spheres. So this theorem is useful in identifying the homotopy types of moment angle manifolds as well. Okay, it's a sphere triangulation. Manifold you get can never look up to homotopy like a wedge of spheres. There's Poincare duality. You must have some cut products or something. But it turns out that it's very common. So equivalently, we're saying that the quasi-linear strand of a Stanley-Reisner ring associated to a sphere triangulation can never be everything, because there's some top class, which has to be a cut product of a bunch of bottom classes. But it turns out to be just extremely common that the quasi-linear strand is everything except the top class of your manifold. So I think I'm not going to write all this down, but for moment angle manifolds, start with a sphere triangulation. That said K is a manifold, but it turns out that your Stanley-Reisner ring has what's called by David Eisenbud and some co-authors that studied these kinds of resolutions, an almost linear resolution. I won't define it, but hopefully you understand what I mean. It just means all of X below the projective dimensions. Everything except the top class, very top degree of X is in this quasi-linear strand. And we show that this happens if and only if K is odd dimensional. So it triangulates an odd dimensional sphere and neighborly. Where neighborly is a combinatorial thing, it just means that every set of roughly n/2 vertices is a face of K. Sort of a high connectedness condition for a simplicial complex. And these turn out to be extremely common. So first of all, Gil Kalai has conjectured that most odd dimensional sphere triangulations are neighborly. And very recently, Zheng, 2024, gave some really interesting asymptotic bounds where, in particular, the number of neighborly simplicial n-1 spheres on M labeled vertices, so on our vertex set M, grows as follows. So it's at least like 2 to the big omega m to the n-1/2. So the number of them grows extremely fast with both the number of vertices and n, the dimension of the sphere. So I just want to pause here and point out how crazy this conjecture is. If you think about, or if I think about just like randomly choosing a sphere triangulation, picture S2, just so that you can picture it. I think if you just threw a dart at the world of all triangulations of a sphere, you're going to get an extremely fine triangulation, right? Where you just randomly choose one. It's not going to look like the boundary of a simplex. That's one way of triangulating a sphere. Much more common, you pick one at random, it should be looking like this, right? Like a very fine triangulation. And that would be very, very far from being neighborly, right? Because for example, any vertex over here and any vertex over here are not connected by an edge. And this neighborliness implies that there are no missing edges and there are no missing triangles, there are no, right, all the way up to half the dimension of the n. So it's really bizarre. Your intuition in low dimensional, in low dimensions is just apparently completely wrong. Notice also that you can start with a sphere triangulation, construct many, many more by like stellar subdividing a face. You start with any sphere triangulation and you just stellar subdivide one facet by introducing one new vertex, then what you get is definitely not neighborly, right? Because this new vertex you've added is disconnected from like everything else, very far from being neighborly. So all of those ways of constructing new sphere triangulations on a higher number of vertices are apparently just completely overwhelmed by the number of new neighborly ones that come up when you go one number of vertices higher, or one dimension higher, and so on. Also, weirdly, these asymptotics are like kind of close to the best known upper bound on just the total number of sphere triangulations. So there's something called Stanley's upper bound theorem, which implies a certain bound, just the complete number of ways of triangulating an n-1 sphere with m vertices. It's in some sense not very far from this. Yeah.
What is omega?
I had to review some big O notation because I don't use this very often, but it's like big O notation, but a lower bound, yeah. So asymptotically, it grows faster than this is all I'm saying. Big O, big omega, and big theta, whatever. Okay, so final thing. So knowing that the quasi-linear strand, which we know is in the image of the Hurevich map, knowing that that's everything below the top class, that's enough to identify the rational homotopy type anyway of a moment angle or of any manifold. So this is going to be some connected sum of sphere products. And without rationalizing, okay, some manifold with a property that it's like n-1 skeleton is a wedge of spheres. So this is also enough to identify its loop space homotopy type, just integrally as a product of spheres and loops on spheres. Okay, so I'll stop here, but we really prove this for a much bigger class of spaces. So there's a class of sphere triangulations called almost quasi-Cazul. Remember, quasi-Cazul, just a complicated word meaning quasi-linear strand. It's everything. Almost quasi-Cazul means that it covers everything except the top class, whatever. So that class actually contains all of these odd dimensional sphere triangulations. They also contain the boundary complexes of stacked polytopes in that first theorem I mentioned, boundary complexes of all cyclic polytopes, and lots of other ones. And this class, unlike the class of neighborly triangulations, is closed under connected sums of simplicial complexes. And in particular, when you take a simplicial complex and you connect sums, or just glue along a facet with a simplex, that's exactly what stellar subdivision of a facet is. So it's also closed under stellar subdivision, right? So we said that immediately takes you way outside of the class of neighborly triangulations, but they'll still have this property that the quasi-linear strand is almost anything. So there's some huge class of complexes, which are at least conjecturally, in the odd dimensional case, most moment angle complexes. So this suggests that maybe most moment angle manifolds are formal. Being able to identify the rational homotopy type in this terms implies it's a formal manifold. And this contrasts with some results of Denham and Suchu, where they look at Massey products in just all moment angle complexes, not just manifolds. And they show that it's like generic that you get non-trivial Massey products. So among all moment angle complexes, usually not be formal. So in particular, usually not wedge of spheres. But it seems when you look at the manifolds, formality seems to be sort of typical or generic. Okay, anyway, thank you. I'll stop.